Alright, again, here we are in parallel RC circuits. This time we are just going to look at the arrows, so the theory behind the map. We're not going to do any of the numbers for this one, and we're going to look at frequency both increasing and decreasing. Alright, so let's get started. So we're going to start with frequency increasing. Now we know that 1/8 is smaller than 1/4, so we are expecting our ohmic values for our capacitors to decrease. And they do. Now we are also expecting our total capacitive reactance to decrease. Remember, it's a reciprocal formula. It's going to be smaller than the smallest value. If both of them are going down, then we are expecting it to be smaller. Again, reciprocal formula, we are expecting impedance to be smaller than the smallest value. If we are putting in smaller value, we are expecting a smaller one out. Now, if the total ohmic value of the circuit goes down, we are expecting current to go up. And then if current is going up, we're going to take a look at all of our branches again real quick. We know that current is going up through our two capacitive branches. That's where current is seeing the increase, because both of those ohmic values are going down. Both of those currents are inversely proportional to that and are going up. So branch 2 and branch 3, both of those currents are increasing. Now we know the ohmic value of our resistor is not affected, nor is voltage. So if both of those things are not affected, the current through our resistor should be staying the same. So we reflect that. We see the current through our resistor staying the same, and both of our capacitor currents increasing. Of course, the voltage on our components is not going to change. Remember, you put one lead on one side of the component, one lead on the other side of the component. It's the same as putting it on either side of the voltage source. Remember, those wires are conductors, and there's no measurable, in this case, ohmic value between the points for, say, this positive side here, any of these positive sides. There's no measurable ohmic value in this conductor. Just like on this side, this negative side down here, or this at the bottom, there's no measurable ohmic value difference between any of these. And so anywhere you put your meter, as long as it's on either side of your component, you are essentially reading across your voltage source. All right, let's take a look at the next one. So here we go, same circuit, and this time, of course, we are going to have frequency go down. Now we know that 1/2 is bigger than 1/4, so we are expecting the ohmic value of our two capacitors to go up. And then because the two values that we are putting into our reciprocal formula have both gone up, we are expecting that total capacitive reactance to go up. Again, we are going to see it be smaller than the smallest value, but now that smallest value, or one of the values, is going up, and so we are expecting that total to see an increase as well. So our total ohmic value is going up. With our total ohmic value going up, we see a decrease in current because they are inversely proportional. Now that decrease in current comes from branch 2 and branch 3. Because the ohmic values and the capacitive branches are going up, we see the current through both of those branches going down, which is what is driving down total current. Now, of course, the voltage and the resistance for branch 1, neither of those change, and so we don't see a change in the current for branch 1. And I put those arrows up for you. Again, voltage we'll expect to stay exactly the same because all of those components are single components in a branch. All right, and that does it for a quick recap of the theory part behind our parallel RC circuits. We are going to do one last video, and that will be a multiple component in a parallel branch. So you can see how that works into the calculation.